Hey everyone, so I'm doing a multi-part series, who the heck knows how long this is going to be, exploring the nature of string theory and the history of string theory. If you haven't watched the previous videos, you should do that, or you can just jump right in. I'm not your boss. But today I'm talking about extra dimensions. In the 1960s, when string theory first came on the scene as a failed attempt to explain the strong nuclear force, something interesting popped up in the mathematics, and that was that it required extra dimensions in our universe. But our universe doesn't have extra dimensions, so what's up with that? How does that work? Well, string theorists, even in the 1960s, were able to point to some earlier research to say that they weren't as crazy as they sounded. And this earlier work goes all the way back to 1919. So it's interesting when we talk about string theory and the roots of string theory, we're talking about ideas that were first percolating 100 years ago and then would lay dormant and then rise again as it was incorporated into string theory. And this idea that string theorists pointed to in 1919 was due to a guy named Theodore Kaluza. This was a couple years after Einstein published general relativity. Theorists around the world went nuts because it's a really cool theory and there's lots of cool things to play with. And Kaluza, along with a few other people, they were looking at general relativity and they're like, general relativity doesn't really say anything about the number of dimensions of the universe. There are 3 spatial dimensions and 1 dimension of time in our universe, our 4-dimensional space-time and general relativity. You just plug that in. You have to tell Einstein that we live in a 4-dimensional universe, and then he'll give you the equations of general relativity and how gravity works. But if we lived in a universe with 14 spatial dimensions and 3 time dimensions, general relativity just, math gets a lot harder, but it still does its thing, no big deal. So Theodore Kaluza was playing around with these ideas. It's like, what happens when I add an extra spatial dimension? Well, nothing much. You just get general relativity in 5 spatial dimensions. But then he started getting really, really interesting. And he said, what if this extra dimension is curled up on itself? Just for fun. We're just playing math games, and math games are fun, right? Yeah, they're fun. What if there's this extra dimension in the universe, and it was wrapped around like the surface of a cylinder, or like the surface of the earth, where you can go in one direction and you'd end up exactly where you started. It's an extra dimension and it curls up on itself. Okay, whatever. But something interesting happened when Kaluza did this. He didn't just get the equations of general relativity, but in 5 dimensions. What he got were the equations of relativity in 4 dimensions, plus the equations of electromagnetism. He got Maxwell's equations. Yeah, that's kind of weird. By adding an extra dimension and making it curl up on itself, just out pops electromagnetism. Now, this is weird. I mean, our universe doesn't have an extra spatial dimension, but yet if it did and it was curled up on itself, you would get 2 theories of physics, electromagnetism and gravity, housed under the same roof, which is something we've been trying to do for a little bit of time now. What's going on? That theory of Kaluza's ended up going nowhere, because once you actually try to introduce, say, electric charge and see how, say, electrons or stars will operate in that universe, all the mathematics breaks apart and you can't do anything. So it wasn't really actually predictive. It was just intriguing. Now, with 100 years benefit of hindsight, we see that the essential feature was that what he called the cylinder condition, that this extra dimension needed to wrap up on itself. That introduced a certain kind of symmetry into the equations, and this is the same symmetry that's baked into the equations of electromagnetism, so it 100 years later, we're like, yeah, of course it showed up because you kind of put it in without realizing it. That's what he was doing, but they didn't know that at the time, so whatever. So it just dropped, it faded away. But then a few years later, Oscar Klein was looking at this, and Oscar Klein knew about all this quantum mechanics stuff, and he was looking at Kaluza's ideas. Like, I wonder if I can get that a quantum mechanical interpretation. Like, what would it mean for this extra dimension to be closed, wrapped up on itself in a quantum universe? And so he started taking Kaluza's idea, and he plug in, various constants of nature. Like, okay, things have to be quantized because we live in a quantum world. We know the value of the electric charge. We know blah, 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 the speed of light. And what he found was that a quantum mechanical interpretation of an extra dimension meant that this extra dimension had to be really, really, really tiny. It had to be somewhere around the Planck scale, which is like 10 to the minus 30 meters or some small number, some incredibly small number, like way smaller than the smallest possible thing in our universe. But that's where this dimension had to be. Now, what does it mean for a dimension to be curled up? Like, could we have a universe with a small curled up dimension? It's not ruled out by experiment. Obviously, if it was large, well, we kind of notice by now. But if it's small, it doesn't even affect subatomic interaction, so there's no way for us to know. And what would it mean living through in a universe with small curled up dimensions? It would mean that at every point in our three-dimensional space, there's a tiny curled up dimension. As you move around, as you wave your hand in the air, you're actually circumnavigating those dimensions, that extra dimension, over and over and over and over again. So instead of just smoothly moving in a straight line like this, you're actually making little loops, loop, 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 loop. But it's at such a tiny scale you don't even notice. The analogy I like to use is, those rollers at airport security when you got your bin, you push your bin down, your bin moves in one direction, but there are all these little rollers that the bin is circumnavigating. It's circumnavigating a second dimension as it's going in one straight line. That's helps me think about it. And in the 1960s, the string theorists were like, hey, there might be some extra dimensions in our universe. They are able to point at the work of Kaluza and Klein. The unification of the forces due to extra dimensions, that was more of a red herring. But the fact that there could be dimensions that were small and curled up, that was the real handy thing for the string theorists, and say, hey, if we need extra dimensions, they're right there. We just haven't seen them yet. Thank you so much for watching, and next week we will continue our exploration of string theory and what it means for strings to actually be vibrating inside of extra dimensions. In the meantime, please go to patreon.com/pmsutter, like, share, subscribe. Just, exist in your extra dimensions. Just feel it. I want you to stare at your hands like this in public. And when people ask, just say you're searching for extra dimensions. I'm sure that will go over well.